This is section 13.6, cylinders and quadratic surfaces, or quadric surfaces. There's two words for it, they mean the same thing. The goal here is we want to be able to sketch some things in 3 dimensions. They won't be functions really, but we'll have an equation, and if you have one equation in space, you get a surface. So we'll be practicing graphing some surfaces. This section is pretty funny because you get to watch me try to draw things in 3 dimensions, and you also get to try to draw things yourself in 3 dimensions. Then we'll also actually try to get the computer to draw them because we have that ability, so we should use it. Anyway, let's jump right in. So at some point, I'm not sure exactly when you are supposed to have learned all about conic sections, but the conic sections are ellipses, hyperbolas, parabolas, and circles. There's also a couple others. The main thing is if you have just back in 2 dimensions, if you had x squared and y squared, you would either get a circle and an ellipse, or you'd get a hyperbola. And the way you can tell is if the x squared and y squared had the same sign, you got an ellipse. And if the x squared and y squared had opposite signs, you'd get a hyperbola. If you, instead of having x squared and y squared, like only one of them was squared, then you'd get a parabola going one way or the other. Now, the main way that you graph these, once you've decided what the shape is you notice that with things like this, x squared over a squared, that x equals a is important. And not just x equals a, but also x equals minus a. So noticing what x's and what y's are important in these let you graph them much more easily. So like here, if you plugged in x equals a or minus a, then you'd get 1 plus a thing equals 1, and those would come with y equals 0. And similarly, if you plugged in x equals 0, you could get x equals 0 and y equals plus or minus b. So the tricks to dealing with equations like this, the main overarching tricks for these, were notice what are some important x's and y's to plug in, and then imagine what happens when you plug in 0 for one of the variables. So like for a hyperbola down here, if you just tried to imagine, well, what happened, let's just take this one, what happens when y equals 0? When y equals 0, you get that x is plus or minus a, and that works. And then what if you try x equals 0? If x equals 0, you get a negative square equals 1, and that doesn't happen. So to graph the starting points for this hyperbola, you'd get that y equals 0, x equals plus or minus a, and then you'd know that the points are not here, that there's no point here on the hyperbola. So that tells you that the hyperbola must go this way. There's a bunch of other tricks to dealing with hyperbolas and ellipses and so on, but we'll use that basic idea of plugging in 0 for some variables and looking for important values of variables to get the graphs. Okay, the goal is to get into 3 dimensions. So let's try to get some things from 2 dimensions and extend them up to 3 dimensions. First, in 2 dimensions, the graph of y equals 3 was a horizontal line. All the points were y equals 3. So you can think of it as you take the point 0, 3 on the y-axis, and y equals 3 is you grab that and you move it side to side, and you get the graph of y equals 3. So x can be anything as long as you keep y equal to 3. Here, in 3 dimensions, what it looks like when a variable is missing. So y equals 3 was missing x. That meant x could be anything. X equals 30 doesn't change anything about y equals 3. So when the variable was missing, it meant that variable can take on any value. Here, in 3 dimensions, if you have x squared plus y squared equals 4, that means that z is missing, and so z could be any real number. So when you graph x squared plus y squared equals 4, that's a circle with radius 2, in the xy plane. But then z is not mentioned in the equation, so z can be anything you want. So you need to take this circle and drag it around at every z value. So up here, it's also x squared plus y squared equals 4. And down here, it's also x squared plus y squared equals 4. The graph of x squared plus y squared equals 4 is all these circles all tied together. And that gives you a cylinder. Notice that it's a surface. It's not the inside of the cylinder. It's just the surface of the cylinder is what we're talking about when we say a cylinder. Now, this word cylinder, we end up using it for more things than you're used to. In like three-dimensional geometry, a cylinder is anything that you can make by starting with a curve C. So like here's a curve C. And then drawing all the lines parallel to a certain line that go through this curve. So if you take this curve C and you take a line that goes through this curve C, and then you take all the lines parallel to that that also go through C in the same, what you'll get is like a bunch of copies of this curve. And you normally would not probably call this a cylinder. But we think of this sheet as it's called a cylinder because it's made of a bunch, like this sheet. It's made of a bunch of vertical lines that are all parallel to each other, and you picked like a base curve and you drew all these lines through that curve. So lots of things are called cylinders, not just these circular cylinders. But a circular cylinder that we're used to counts as a cylinder because it's got all these lines. And all these lines go through this base curve, which is this circle. These lines, they're called the rulings, these ones. Not the, oh no. Okay, so over here, these are the rulings. And over on the weird example I gave you, it's the parallel lines that are the rulings. They have to be actual lines, not the curvy ones. Okay, let's try to graph a cylinder that's not like the usual cylinder. This one has X and Z mentioned, but Y is not mentioned, so Y can be anything. So get your coordinates, your coordinate axes going, X, Y, Z. Y can be anything. Let's start with Y equals 0. And when Y equals 0, we get this circle of radius 3. The trick to drawing this, a circle that's like at an angle like this, I mean, I didn't do a great job, but the trick to drawing a circle that's at an angle like this is at the top, it should be flat, and flat means parallel to this x-axis. So at the top and at the bottom, it should be parallel to the x-axis. If you just draw a circle like this, it doesn't look right. Anyway, this is the circle at y equals 0. Because y can be anything, you actually like can go anywhere in the y direction and get more of these circles. This one circle that we started with, we can see now that this part is in the background and not visible. So this one also ended up being a circular cylinder. I don't know. I think probably the best way to show that something has an inside and an outside is to draw a line that is coming out of the middle of it. In this case, the y-axis just like shoots out of the cylinder. And if you draw what it does, like the y-axis is mostly invisible here, but then it becomes visible here. And that line helps us see what's going on here with these, with the cylinder, that it's like open here. It's just a drawing trick, but these drawing tricks can be helpful in this class. So I'm not like the world expert in drawing, but basically if you're drawing a cylinder and you're trying to make it clear that like you're looking into a, like a hollow cylinder, then it helps to draw the axis that's like going through it, and then people can see what you're talking about. Okay, that's x squared plus z squared equals 9. Do something else. Here's z equals y squared. Here, x can be anything. So what we'll do, since x can be anything, I'll say, well, for now, x will be 0. Draw my axes. Let's start with x equals 0. Z equals y squared is a parabola. But then we take that parabola and we put it at every x coordinate. So we'll have one here, and one here, and then connect the corresponding points. So what we have is it's a cylinder. The rulings are this way. They're parallel to the x-axis. Let's do better. Yeah, it's just like a sheet of paper that's been folded up. How about z equals sine x? Well, here y can be anything. This is called a cylinder because one of the variables is just left out of the equation. So I'll start with y equals 0, and then I'll draw the result at every value of y. So here's x, y, and z. Z equals sine x. Well, at y equals 0, I'm in the xz plane, and I have a sine function. So it's going to be like, oh no. Like this. But then this sine function, well, it happens again over here. And again over here. And you connect the corresponding points as best you can. These connections are the rulings. And here, because y could be anything, these rulings are parallel to the y-axis. So what you've got is just like a, I don't know, wavy, this is what cylinders look like. Just make it wavy. Okay. I'll do one more by hand, and then we'll look at a couple of them drawn by a computer. So how about y equals e to the z? Y equals e to the z, x can be anything. So I'll do x equals 0 first. At x equals 0, we're in the yz plane, so I'm just in the plane of the paper. It crosses at z equals 1, and has an asymptote of the y-axis. So I get this thing. But then this thing has to happen at every x value, because x is not mentioned. So you go over by 1, and you make another copy of it. And you go over by another one and make another copy. And you do this at every x value. Then the rulings are these connections, and the x can be anything, so you should make your rulings parallel to the x-axis. You can see that it's an exponential function, but it's been turned into a cylinder. What happens on the graph near the xz plane? I don't think that's the question that was intended to be asked here, because nothing special happens on the xz plane. I guess on the xz plane, well, whatever, we can just answer the question that's there. On the xz plane, y equals 0. This looks bad. On the xz plane, I get y equals 0, so 0 equals e to the z, but 0 equals e to the z has no solutions. So I think I've not graphed the right thing here. because the xz plane, my graph just has z equals 1. So what did I do wrong? Oh, I graphed z equals e to the y. Y equals e to the z would go like this. Ugh, that's too bad. Okay, well, whatever. I'll just leave it here. This is z equals e to the y. Let's just get a different color. Y equals e to the z would go this way instead. Crosses out 1, though. I can't hit it. There it is. Y equals e to the z would be this one, where you switch. If you switch y and z, then they switch. You like reflect it over the y equals z line. In this case, it's a plane, but anyway, you get a different shape, of course. It's down here. And the xz plane in this case is not going to have, it's the xz plane is like an asymptote for this. So this is y equals e to the z. Okay, let's get the computer to draw a couple of these. The main thing you were supposed to take away from this, though, was if there is a variable missing, that variable being missing from the equation means that that variable can be anything you want. So you set it equal to 0 first and draw the shape, and then make a cylinder out of that shape. Anyway, we're going to go to geogebra.org/3D. I should really write that down when I switch to it. So we're going to geogebra.org/3D, which is the best free 3D grapher. And then we can just type some of this stuff in to make sure that we have the right pictures. So like z equals y squared. You type it in over in the left side, and then you can kind of like grab it with the mouse, hold down the mouse and move to the left and let go, and it'll rotate it to show you what the shape is, to see if you like did a good job. Our positive x-axis in our picture was like this way. So this is what we should have drawn. And here's what we had. That's like pretty good. Oh, that's not bad. Let's try z equals sine x. Z equals sine x is this like wiggly sheet, and the rulings are parallel to the y-axis. That's these straight lines. Those are the rulings. I mean, looks like a 3-year-old tried to draw it. Oh well. And then let's get y equals e to the z, which should be this orange shape. And then I'll also get z equals e to the y to show what my mistake was. Y equals e to the z. And let's do z equals e to the y. This one didn't work at all. This one is not doing what I want it to do. I'm not sure what it's doing with the F there. So I'll just make a new one. Where's y equals e to the z? Does it need a better color? Huh, I don't know why it's not showing up. I shouldn't spend any more time in the video trying to figure it out. Oh well, I don't know. Maybe it has trouble thinking of z as the independent variable? In that case, this is not a good grapher. It does kind of look like it just doesn't know what I'm talking about here, though. Like I've typed it in wrong somehow. But this looks fine. And then when I click away from it, it is confused. So, I don't know. If you're interested about this, we can fight through it in an office hour, or you can send me a question or something. But in general, GeoGebra should be able to graph this, and I guess I've messed something up, and I'm not sure what. So we'll just move on to the next thing. I don't want to waste your time. Okay, so those were cylinders. That's like half of the surfaces that you're expected to draw. The other surfaces that you're expected to draw are the ones that are curvy in every direction. And there are lots of different surfaces. You should not think that this is all the surfaces. If we type random stuff into a grapher, we should be able to get like all kinds of weird shapes. Let me go back into my grapher. Like if we just do like x cubed plus y squared minus z equals 3. Maybe it just doesn't know how to do this. Like maybe you have to solve for z. Okay. Yeah, that's too bad. Okay, so GeoGebra is not amazing after all. But like here's z equals x cubed minus y squared plus 3. It's some weird shape. I don't know what this is. Could be anything. You could put y squared sine of x in here. Now it's like all over the place. Who knows? There's tons of surfaces, and if you type any random thing in here, you should be able to get like a really weird surface. But there's certain surfaces that are really nice and easy. Those are the quadric surfaces, and they come up occasionally, so you have to figure out how to draw them. It's basically like when we found ellipses and hyperbolas and parabolas, but like you can kind of have ellipses in one direction and hyperbolas in the other direction. In that case, you would have this hyperboloid. You have like some ellipses if you look from this direction. Like if you go around this surface, it's ellipses. But if you look at the other way, you get hyperbolas. And that's called a hyperboloid. Here we've got an elliptic paraboloid. That's where if you look one way, you've got parabolas. But if you look the other way, you've got ellipses. If every way you look, it's ellipses, so like ellipses this way, ellipses this way, then it's an ellipsoid. And these all have different equations. In most cases, we're only dealing with anything where the variables are squared, and that's what makes them called quadric surfaces or quadratic surfaces. To get a parabola, you do some variable equals the other ones squared. To get an ellipsoid, you have all the variables squared and all the same sign. To get hyperboloids, you can have, so you get it equal to 1 on one side, and then you have 2 of the variables squared and positive and the other one negative. That gives you this kind of hyperboloid. It's one connected sheet. The other way is, here's another kind of hyperboloid where it's a hyperbola in this direction, but it's an ellipse around, but it's in 2 pieces. This is a hyperboloid of 2 sheets, and when you get it equal to 1, you end up with 2 negative variables. There's a bunch of others. This one is a cone, except it's ellipses if you cut this way. And then the weirdest one is the hyperbolic paraboloid. The hyperbolic paraboloid is also known as a saddle because it's got like parabola this way, hyperbola is this way, but also you can imagine like a person sitting in it. It's a saddle. So let's practice drawing some of these. Essentially, you'll just refer back to this. If you have the book or an ebook version of it, you want to look at page 862 and you get more. There's more info about exactly how to find what's going on. But let's just try to draw some of these. The easiest way that we will have to draw them is the same way that I showed you before in 2 dimensions, which is just plug in 0 for something. When you just plug in 0 for something, you get things called the coordinate traces. If you plug in z equals 0, you're looking on the xy plane. If you plug in y equals 0, you're looking on the xz plane. So this box looks very fancy, but it's actually just the strategy. Just plug in 0 for something and see what happens. And that's called coordinate traces. So we draw some coordinate traces and then try to connect them and see what shape we get. So this one, I'll do the XY plane. The XY plane has z equals 0. When I plug in z equals 0, I have an ellipse. And the ellipse is x squared over 9 plus y squared over 25 equals 1. For this ellipse, I know that x goes from -3 to 3, and y goes from -5 to 5. And I can see that by just like imagining, what if x was 0? Then y would be -5 or 5. What if y was 0? Then x would be 3 or -3. So in the xy plane, I go out to 3 and -3, and I go up to 5 and -5, and I get like an ellipse that's taller than it is wide. Then you just do this for all the planes, and hopefully that's enough for you to piece together what the overall picture is supposed to look like. So the xz plane, y is 0, then you get a different equation. It's still an ellipse. It's x squared over 9 plus z squared equals 1. This will be in the xz plane. In the x direction, you go out by 3, but in the z direction, you only go out by 1. So it's like not very tall in the z direction. And then the yz plane, you plug in x equals 0, and you see that it goes all the way out to y equals plus or minus 5. So it's like really long in the y direction, and it's really short in the z direction. If we put all this together, we can try to draw it, and it won't be a total disaster. In the xy plane, we go out to y equals 5 and y equals -5. X equals 3 and x equals -3. Remember, when I draw this ellipse to connect the dots, at the edges where it's flat, I want to be parallel to the x-axis. So like, it's not going to look like this at the edges. At the edges, it's going this way, the way that the x-axis is going. And that's how you can get your 3D pictures to look vaguely correct. It's still mostly a mess, but basically parallel things stay parallel in perspective. So this is my trace in the xy plane. In the xz plane, I know it only goes up to z equals 1. So in the xz plane, it's like really, really short. And now I can start to see that like, oh, some parts of this are not really going to be visible. In the yz plane, well, it's just the same info. So I've got this, I don't know, potato. It's like even more squished than a potato though. So it's an ellipsoid. Let's try this hyperboloid. This one is a little bit weirder. So this one, when I plug in x equals 0, I'm looking on the yz plane. X equals 0 gives me a hyperbola. Let's just try to draw it. Here, if z was 0, I would get nothing. This has no solutions. If y is 0, z is plus or minus 3. So hopefully you're seeing the overall plan here, which is that like you're just setting everything to 0 over and over until you can get a handle on what's going on. If you remember how hyperbolas work, this fact that y goes from -1 to 1 is you get to like draw this box, and the lines that go through this box, through the corners of this box, give you the guides to draw the hyperbola. So it's kind of like squeezed real thin in the yz plane. I don't know, let's just try another one. Let's try y equals 0. For y equals 0, we're in the xz plane. And in the xz plane, I have both squared and both positive, so I have an ellipse. This ellipse goes in the x direction from 2 to -2, which I can see this way. And in the z direction from 3 to -3. So it's like pretty round. It's a pretty round ellipse. I'm not going to draw that one. It's like mostly a circle. For z equals 0, I'm in the xy plane. In the xy plane, I have another hyperbola. This one, let's draw x and y. If y is 0, I get x is plus or minus 2. And if x is 0, I get no solutions. Draw my little box, get my lines here, and then I can draw my hyperbola this way. So I'm going to have, like, the slices in the xy plane are parabolas, the slices in the yz plane are hyperbolas, and the other slices are mostly round ellipses. So let's try to put it all together. X. I kind of want more space than this. Do I get more space? Ooh, I do. Okay, so in the xy plane, I'll just draw that first because it's like flat on the ground. I go from -2, oh no, I don't go from -2 to 2 that way. I go -2 to 2 in the x's. And there's actually points there. And then there's like, it's kind of like thin in this direction. In the yz plane, at x equals 0, it's also kind of like squeezed in thin. But it goes to z equals 3 and z equals -3. Now, how are we going to connect these? Well, in the xz plane, I have x squared over 4 plus y squared over 9 equals 1, and that connects all of these points. So what's going on here? What's going on here is that this like needs to, it's got circles that are this way, and the circles need to like expand out to catch the expanding hyperbolas. So the corresponding points that get connected are like these ones, the ones that are farther out. And then these arrows are the ones that are farther out. So it like gets, it's like a, I don't know, it's like the usual picture of a wormhole where like it gets smaller and then it's going to expand out again on the other side. So the picture is going to be like, it's got like the entrance here, and there'll be an exit over here. And you kind of like do this. I think you can maybe see it. The inner circle here should be like, this is like the small circle that's here in the center of my original picture. You should kind of be able to see it here. I think that's the best picture I'm gonna get. It's this here. But these outer circles that I drew are kind of a disaster. Well, this is the level of work you're expected to do. You're supposed to get some coordinate traces and then know what the general outline of the picture looks like. Let's see if GeoGebra can do this. If not, it's going to be pretty sad. So we're doing I'll do the first one and then the second one. Okay, I guess we delete. So I'll say x squared over 9 plus y squared plus z squared over 25 equals 1. Is that what it was? Oh, no, the y had the 25. What we get is this like really flat, I called it a football that had been squished. It's not bad. It's like kind of fine. So this is the picture that the computer gives us, and that's compared to the picture that I was able to build with the coordinate traces. And that's like pretty good. But now we get into like this hyperboloid that has one sheet. I concluded that it must look kind of like this. Let's see how we did. X squared over 4. Z squared over 9, and then minus y squared. Okay. Well, this explains why I had trouble drawing it to scale, because to scale it's like completely absurd. Man, this is hard to see even when the computer draws it. Well, I feel much better now. But it's like, it's got a little opening in the middle, and it's all connected, one piece, and it's kind of like exploding outward in one direction and outward in the other direction. Man, it's like not easy to see. But this is a hyperboloid of one sheet. Let's keep it moving. This one is a hyperboloid of 2 sheets. If anything really weird is going on, then the question will give you a hint that says, hey, maybe instead of trying x equals 0, you should try this. Okay, well, let's try it. X equals plus or minus the square root of 32. These are planes that are out at certain x values instead of looking at the actual yz plane. And that kind of makes sense because if we tried the yz plane, we would just get nothing. If you plug in x equals 0, you get no solutions. So instead, it's like, I don't know, try this instead. So we try x is plus or minus the square root of 32. When you plug that in, you get 32/16 minus y squared minus z squared over 4 equals 1. And now I want to figure out what is this shape. Well, if I subtract 2 from both sides, I get this. And then all the terms are negative, so when I multiply through by minus 1, I notice that this is actually an ellipse. So out here at this x value, I have an ellipse. Let's try some other coordinate traces. So this was x out at certain x values, like between 5 and 6. Let's try y equals 0. Y equals 0 gives us a hyperbola. Because one's positive and one's negative, both are squared. This one, the x's go out to 4, the z's go out to 2. X, z. If I try z equals 0, I actually get 2 solutions, because I have a square being positive. That's out at x equals 4. And x equals minus 4. If I try x equals 0, I get nothing. But I know that the z's go out by 2 and minus 2. So I have this like box, and connecting the diagonals tells me like how squeezed the hyperbola is going to be. So it's kind of like squished vertically. So this is when y equals 0 in the xz plane. When z equals 0, that's also a hyperbola. One positive and one negative. It's x squared over 16 minus y squared equals 1. And again, if I let x be 0, I get nothing. x equals 0 gives me nothing, but y equals 0 puts me out at 4 and minus 4. So I again end up with kind of like a really squished hyperbola. So this is because I have this like huge open space in the middle where like x equals 0 gives me nothing, and you can see that there's like blank space at x equals 0 everywhere. This is a hyperboloid of two sheets. So instead of being connected in the middle, it's got like a blank space in the middle. So the shape it's going to have nothing on the YZ plane, but out here at x equals between 5 and 6, I get a little ellipse, this one. And same thing at minus 5 or 6. And then I have hyperbolas out there. So it's like little sheets of hyperbolas out there. Can you see that? They're supposed to be like bowls that they're not connected in the middle. And we could tell that there's a big blank space where x equals 0. Let's ask the calculator to try. So we had x squared over 16 minus y squared minus z squared over 4 all equals 1. And here's our two sheets with a blank space in the middle. Let's get the scale closer to what I was drawing. Huh, it is symmetrical, but we've somehow zoomed in a weird place. Well, two sheets, ellipses if you slice it one way, and hyperbolas if you slice it the other ways. I like this section. We end up not applying it very much in later sections. We do apply this plan of being like, let's just plug 0 in for stuff all the time, just to get a handle on what's going on. But yeah, this is supposed to be kind of like a payoff in its own right, so that you know how to build some various shapes. Okay, here's another shape. This is an elliptic cone, apparently. So let's try to figure out what's going on here. The hint is that the traces parallel to the xy plane. Notice parallel to the xy plane, not the xy plane itself. So here's the xy plane is z equals 0. This gives us an ellipse. But let's try some other... Wait, what? Equals 0? That's not an ellipse. An ellipse would have this equals 1. And there's no way to clear the denominators to make the right side equal 1. So what is this shape? How can you square a number and square another number and add them up and get 0? The answer is that this is a point. So on the xy plane, like, you have to be careful about this, that the standard forms for ellipses and hyperbolas have equals 1 at the end. On the xy plane, there's just a single point that everything like comes to a point there. If you instead let z equal plus or minus 1, then you get the 1 that you were expecting, and then you get an ellipse. And as you let z get bigger, you'll get bigger and bigger ellipses. So this is already enough information to draw it. It all comes to a point here in the xy plane. But if you go out from the xy plane, then you end up with ellipses that are longer in the y direction, like out, and shorter in the x direction. So you get like this. And it all comes to a point here at the base. Now, an elliptic cone, it goes both directions. So it's not just going to be a cone. It's going to be a cone that keeps going down in the negative side, because this works just as well for z equals minus 1 as it did for z equals 1. So I hate my picture right now. I kind of want to start over, but let's just let it go. it also expands this way. So if I drew it again, I would probably go like this. And then connect these. And then you can kind of see what's going on. That it's a cone. Yep, so that's that. Yeah. I think there's only a couple more. We just want to do a little bit of each, so there's two more. This one, the elliptic paraboloid here, you can tell this one is different because it doesn't have all the variables squared. So one of the variables is like very different than the others. In this case, if you let y equal 0, like I would focus in on the weird variable here. Y equals 0, I should always try, and I get the same issue as I had before where I get a point. Then there's a hint that tells me what to try for other values of y. Well, when y is 1, I get an ellipse, because I get a 1 exactly where the ellipse is expecting an ellipse, or exactly where the ellipse is expecting a 1. And it's like longer in the x direction. But this time, because y isn't squared, if I try y equals -1, I get -1 equals all this stuff. And there's nothing there. So instead of being a cone that like makes a point and then on the other side something else happens, no, instead I've got a paraboloid. It's only going to be on one side. So I've got a point here. Out here I have an ellipse. It's longer in the x direction, so it's like this, and then it grows this way. So like a parabola that's expanding outward. Is that good? Yeah, that's good. Okay, this one is probably the hardest one to draw. This is a hyperbolic paraboloid. It's going to be a saddle, but the coordinate traces will help us here. So let's try x equals 0. X equals 0, we get z equals -y squared, which is like this. When y equals 0, we get z is x squared over 9. X, z. So it's kind of like a flattened out parabola. And when I let z equal 0, I get x squared over 9 equals y squared. Like if z is 0, I could move this over. When I take square roots, I get x over 3 equals plus or minus y. So y is plus or minus x over 3. So at z equals 0, I have two lines. Notice the square root giving us a plus or minus is really important here. So this is the x, y plane. The hint tells us to try z equals -1. I don't like this -1, so I'll move everything over to the other side. And I get a hyperbola. The hyperbola works with y equals plus or minus 1, and x equals 0. But it doesn't work with the others. So at z equals -1, we can look in the xy plane, and we get that there's points up here, and you get kind of like a hyperbola that goes this way. So how are we going to piece all this together? I've got some parabolas in some directions, and some like lines in others, and some weird hyperbola stuff going on in the last direction. So let's try to put it together. We know it's supposed to look like a saddle. What's the easiest one to draw? Probably the YZ plane, because it's flat on the paper. So the YZ plane I get a parabola like this. And then in the xz plane, ooh, in the yz plane I actually had a regular old parabola that wasn't so flattened. But in the xz plane, it was more like a flat parabola. I'm worried that we're not really going to do much better than this. Like, adding these two lines is death. We don't want that. Like, nothing good comes from drawing those lines. Z equals -1, you can see that like it's going to split into two pieces. I'm not sure what's the best way to draw this. I think z equals +1 would have been better. Because z equals +1 would show us that we want like this kind of action. To give us like somewhere to sit. The problem is the slices are just lines, so it's like a total mess if I try to draw that. Huh. I don't know. I think the best I did was when I just had a parabola and like another parabola going the other way. And that allows you to see that like if you put your legs this way, you can sit on it. Let's see what the computer does. I guess you're seeing what level of competence you're expected to have when drawing this. The main thing is the strategy of plugging stuff in and see what happens. So let's get this saddle point here. Z equals x²/9 minus y². And here's our saddle to sit on. You can see the xy plane when it spins certain ways. You can see the lines, these lines. It's just two crossing lines, which was one of our coordinate traces. But that's not a good thing to add to your picture because it gives the wrong idea of what's going on. So just practice these, do your best, submit some homework. You got to practice this. And then you should kind of feel like there's lots of shapes that can happen in 3 dimensions. The easiest ones are the cylinders. So these were the ones we did early on, where you like draw a curve and then you draw a bunch of copies of the curve moving in the right direction. And when a variable is missing, you can just deal with that easily. That you need to be expert in so you can draw stuff later in the class. The more complicated ones, all the different various quadric surfaces, these are really common quadric surfaces, and it's a standard like outcome goal of the class to be able to deal with these. But you shouldn't like hurt yourself trying to become super expert at these. Instead, the technique of getting coordinate traces by plugging in certain values, that's the technique that's going to come back over and over in this class. There's something called level curves in the next chapter where it'll come up. So like, are you supposed to be able to draw a perfect saddle? No. Will I be impressed if you can? Yes. So see how you can do. But like the simpler ones, you should be able to draw using the coordinate traces. So do some practice. Yeah, do some good work. Good luck.